Hi, my name's Andy, and we're going to do some billion row challenge stuff today. So like performance stuff. We're going to probably try and do like the easy bit today and maybe look at some harder bits another time if we feel like it. Just to deal with the elephant in the room, if you've watched some of my other videos, previously I was not wearing glasses. Today and in future probably I am wearing glasses. I've been wearing glasses to use a computer for a while. And because I have the fonts quite big in these videos, I've been getting away with not wearing glasses whilst recording videos. This evening, it feels like I can't see anything at all. So there we are. Right. So I recently watched a very long, very entertaining and educational video by Jon Gjengset, who I would absolutely recommend if you're into like, hard, interesting Rust stuff. He's really good. And he was doing a challenge called the Billion Row Challenge, which was is a few years old now, and was the thing that happened in the Java world where there was a challenge to get a program to run really fast. And then since that, obviously people from all the other languages wanted to get involved too. So people have been like golfing this massively since then. The challenge is like really nice, seductively simple, just with this very large number involved. So basically what the challenge is that you have a file with data like this in it with a load of, I think these are city names and temperatures. So they're basically temperature readings for what temperature it was in that city on a particular day or something like that. And the challenge is just to go through and aggregate this data. So for everything with the same city name, we want to know the minimum and maximum temperature readings, because there'll be lots of lines that feature this city, and the average, the mean temperature. And just to do that really fast, and the kind of the hook of this is that there's a lot of data. In fact, there are a billion rows of data in the input file. The input file is literally a text file that just looks like this, right? It's just a semicolon separated, and then this temperature reading on the right hand side, and then like some kind of Unicode city name on the left. And there are various, like the rules are quite specific. For example, the file is UTF-8. There's a set number of cities that it'll never go more than, I think, 10,000 cities. And those are the kinds of rules that we'll need to get into when we are looking at the full challenge. But I was watching Jon Gjengset do his excellent videos and crying out for unit tests. Please, more unit tests. But also, there was a particular bit of this problem that I thought was a good piece that we might try and bite off, just to get a handle on one corner of this problem, which is parsing the temperature. So today we're going to try and take lines like this and get the temperature value out of them and try and do it in a quick way. So I haven't done I haven't done any properly systematic performance related work in Rust. Like I tend to find that when I write Rust code, it goes quite fast without me having to do a lot of work. But I wanted to be a bit more principled, especially after someone, I've forgotten your name, sorry. Someone pointed out to me that I destroyed performance in something I was doing the other day when I was trying to improve performance. So I thought I'd give it a little bit of a go at using this library called Criterion for benchmarking Rust programs, and maybe we'll try some other tools as well. So like the perf tool, which is part of the Linux kernel, which Jon uses in his videos. We could maybe a part either in this video or in other parts of the series, maybe have a look at that. And also Cargo ASM, which just displays the assembly language instructions of your program, might help us out here depending where we get to. So I've got set up already just a really like an example from the Criterion crate, which is how to do a benchmark. So just quickly running over that. So we basically say please make me a main method for this group of for this set of benchmarks called benches, And then so we tell it, look, there is one group that I want you to make as part of this set of benches called bench fibs. So basically that just means like find your benchmarks in here. And then these are the like actually do something parts. So basically we say there's a group called Fibonacci, because the test code is just like doing Fibonacci stuff. So in a minute we'll replace this with something relevant to what we're doing. And then basically you call your function, and you also say you give a name to like that call of that function. And I've set it up like this so that we can compare different things. So in this case, there's two different implementations of Fibonacci here. There's one which is recursive, which very slowly calls itself multiple times each time to work out the Fibonacci numbers. The Fibonacci numbers are just the previous one plus the one before that makes the next one, which is what we're seeing. That's what this means basically. So it goes like 1, 1, 2, 3, 5, 8. Just adding the previous two together to get the next one. And then there's a faster way of implementing that without recursively calling yourself. This benchmark, when we run it, looks like this, and it basically says, look, the recursive implementation took 475, I think that's picoseconds, whereas the iterative version, which is faster, took 256 picoseconds. And then there's like these are like the 95th percentile, I think. So basically we can be fairly sure that the correct time is somewhere between 255 and 258, which definitely doesn't overlap with 462 to 491. So we can say with some confidence that the recursive one is slower than the iterative one, right? So anyway, that was just our benchmarking setup that we're going to maybe use. But let's get back to the problem, and let's do like a simple implementation that won't be particularly fast, although it may be pretty fast. So we may find that the stuff we try is no better. So let's do a very simple implementation of a function we're going to call parse temperature, which takes a line like this and gives us back a number. And one other point about this, one of the many insights that people who've already tackled this problem have had is that even though these are floating point numbers, because they're in a very fixed range and precision, it's actually much more efficient for us to treat these, deal with these as integers. So this would be 409, and this would be minus 754, and this would be 44, and this would be 5, and this would be minus 13. And the reason, that's faster because integers are just faster to deal with, I'm pretty sure. And yeah, so it's just easier. So our program is going to return an integer, but I'm now thinking about it and thinking my naive implementation is actually gonna, I think, return a float. So we'll see where we get to with that. So we're going to end up with loads of different versions of parse temperature, which we can then benchmark against each other and figure out which one's fastest. All right, so enough preambling. Let's have a main method that actually does something. So let's do... yeah, so we have some other rules as well. So temperatures are between minus 100 and 100. Temps always have one decimal place. And I believe they always have one decimal place, even if it's like 1.0. Let's double check that point, shall we? We have an actual sample data file in here. Data, I think. Yeah, let's look at I've got a file with the first 100 in just to make it not so huge to deal with. Yeah, so here's an example of a piece of data which ends with a 0. Let's put that in our examples. Yeah, so even if it's exactly minus 23 degrees like this, you still have 0.0. So there's always one decimal place, like so. All right, so let's start off with just a really dumb thing. So let's write an implementation called, by the way, I wrote inline never here so that if we do use some kind of performance tool that like lets us look at how much time each function takes or each line of code takes, we'll get good information on which function is actually being called here. And we shouldn't, inlining this function at the top level, yeah, we might, it might, eventually we might want to inline it, but while we're trying to make it itself fast, I guess we don't want to inline it. It makes sense to me. All right, so let's take an example line. In fact, why don't we, I think maybe our main method should probably just do a few. Let's have 3 like this. So let lines equal something like this. And close the array. So let lines be an array. Yep, and then for line in lines, we'll just loop through all those example lines, and I guess we should we should grab the answer, which is going to, I think in this case, is going to come out as a float, even though I said it wasn't going to, and then we'll print that out. So I guess this would be, should we print the line as well? And then the answer, like so. Now, the parse temperature float function needs to take in a reference to a str, and in this case it's going to return. Now, I think it should return an F6, an F, I don't know, let's make it an F32 because I don't care too much. Alright, so we need to print everything at the beginning. So we have some example data, we loop through the example data, we call parse temperature on each thing, print out the answer. So let's parse the temperature, let's start by returning 0.0 and check it works. Yep, alright, so it indeed does print out the lines, and then the answer we got back, which was 0. Interesting that it prints it out with no decimal point, even though it's an F32, but never mind, we won't worry about that too much. All right, so now we need a test, I guess. So we'll have a kufug test module called tests, and in there we'll have a test. And I guess it should be, let's say, positive. Should we have a positive double digit? No, let's have a positive single digit. Positive single digit. And I think I'm just going to, even though normally test names should be like when this, then this kind of thing, but I think in this case, we basically, all of them are going to be when I parse a positive single digit, then I get the correct answer. So it's going to be a bit boring. So, maybe at some point, maybe we should parameterize these tests for, and we can run all the tests against each of our different implementations. That would be nice, wouldn't it? Yeah, we should do that. All right, for now we've only got one function, so we're just going to do it. All right, so we're going to do parse temperature float on a line, which is a single digit positive temperature. So we'll have this one here. Now, we're assuming that these lines have no new line at the end. So whatever work we've done to parse the sample data that we were given, which is a load of lines with new lines at the end, we've ended up with ampersand strus, which don't have a new line at the end. So don't yet ask me how we did that. That's for another day. But yeah, when we parse this line, we should get back 4.4. And I guess we should do another example, shouldn't we? I guess we've got one here. So let's do the one that comes out as 0.5 as well. like so. 0.5. Now, our test will fail because we haven't implemented anything yet. Also, floating point equals is a bit awkward, isn't it? So we need to run cargo test. And wait for it to build. Yeah, so in these cases, 4.4 and 0.5, we're explicitly giving a float on one side and we're going to be returning. I don't know whether we can get away with exact equality for these floats. And normally, I would care about this and I'd go away and get it sorted somehow. But because most of our functions are not going to be returning floats anyway, I don't care too much. That as long as these tests pass, I'm going to just pretend it's fine to compare floats exactly, even though it's generally a really bad idea. Okay, so our test's failing because so far we would just return 0.0 every time, so it's definitely not returning 4.4. So let's do a really dumb implementation. This shouldn't be called float. This should be called... no, the point is it's using F32. So what I'm going to do is do an F32 parse. I think that's... Is that how you do it? Does that actual thing exist? No, I think it should be something more like we're going to split the line. Let's split the line first. Let's not get ahead of ourselves. So we're going to do split at, and then the place where the semicolon is, and that's going to give us two things. Is that right? Split at returns something we don't care about, and then temp, I think. Is that right? The split at return. Oh, I need an equals sign. I think split at should return split at returns a tuple. So basically we're going to split the line where the semicolon is, and then get back a temperature, which is an ampersand str, and then we're going to do temp.parse, and I think it knows. All right. Okay. So first problem we have is that this might fail. So parse returns a result, whereas we want to return just an F32. And I think it's correct to return an F32 because the rules of this game are that the file format that we're parsing, the file that we're parsing won't have any errors in it. So we can panic if there is an error and just say, we don't care. So maybe panicking will be the wrong thing to do at some point because it might be a bit slow to have like panic mechanisms in there. I'm not sure. Maybe just that we can abort on panic and then it hopefully won't cause any slowdown. But right now, I think the kinds of performance gains that we're looking for are not going to be... just everything we do is going to have like stuff like that. We're not going to bother optimizing stuff like that. We're not looking for some kind of absolute time for a billion lines, which is where we would have to think about like compiler flags and stuff like that. We're just going to be looking for the code that we're writing. Can we make it faster? So this should be unable to parse. Float. That'll do us for now. So what we're saying is call this parse function, which basically means turn a str into something else, and because the return type of this function is F32, it knows I want you to turn this str into an F32. So now we need to just say where do we split the line at to find that semicolon. Now what happens with split at, because the mid should be byte offset. The two slices returned go from the string slice to mid and from mid to the end of the string slice. So we actually want to go, we want temp to not to contain a semicolon. So I think we want, assuming temp does contain the semicolon after we've done the split at, then we want to take a slice of temp which skips the semicolon, parse that as a float. I think. So we better find the semicolon, haven't we? I've been assuming all this time that you can find a semicolon. So let's say semi I equals line dot find. Yeah, and our pattern that we're going to pass in is going to be just the semicolon character. And now line assumes that we might not find one. So it returns an option, but actually, find assumes that you might not find one, but there should always be one. So we're going to say no semicolon in line. And just crash again. Because we expect the file format to be exactly predictable, this should always work. Because of the beauty of UTF-8, looking for a semicolon will never match some part of some other letter or anything like that, even multi-byte letters, multi-byte characters. So just doing a find on the semicolon character should find it. Now, there's a lot of stuff we can improve about this implementation. For example, this semicolon is actually equivalent to a U32, so it's like in UTF-32 encoding in some sense. So looking for that character, what I'm trying to say is we could be looking for a byte in a byte. A set of bytes instead of looking for a semicolon in a str. And like some implementation, if we do it in future and find that this is a good implementation but needs improvements like that, that would be one of the improvements we might be able to find. But this is just our example implementation of kind of a dumb, slow way of doing it. So far we're not going to worry about it. So let's see whether our tests pass. Our tests passed. Okay, so positive single digit came out okay. Now we've actually probably made a whole load more tests pass. So let's make a few more. What about a negative single digit? So that would be, an example of that would be this one. So that's going to should come out as minus 1.3. Just have one example of that. Run that test. That passes too. All right. I guess we should make it fair just to make sure it's really testing something. Yep, it worked. Okay, so let's also do a few more examples. So I guess we're going to do positive and negative multiple digits. Is that all the examples? I guess it probably is. There's not too much to this, right? So, positive multiple digits, here's our example of that. So, that should come out as 40.9. And negative multiple digits, we've got a couple of examples of that. So, we may as well have them both. What did I do up here? Okay, yeah. So again, that's going to come out as minus 75.4. And this one with a nice long name to make sure that we handle the spaces in names and things like that. Comes out as minus 23.0. Okie dokie. Where are we at then? So let's see if our tests pass. Yes, all our tests pass. Right, so this implementation that we've written, which probably isn't particularly slow, seems to pass our tests, and I think that's enough tests. Like, we're only bothered for this video, we're only bothered about passing the temperature. We know temperatures are always, I actually think the temperatures are always between 99.9, minus 99.9, 99.9, but I could be wrong about that. But we're going to assume that at least for this video. They definitely always have that one decimal place, and that will be important in some of the later implementations, although it wasn't a problem for us here. Okay, so now let's try and benchmark this parse temperature float function. So we're going to get rid of these implementations here, and we're going to benchmark just one thing, which is parse temperature float. which we'll have to bring in from our crate, which is called brum. That's like a funny joke. Because Jon Gjengset called his brr, that's hard to say. And a little more British way of saying it would be brum. Okay, so hold on, that's not working. How do you bring in your dependencies on the current crate? Oh, I tell you what, I know why that's happening. All right, we'll fix that in a second. So parse temperature float is going to need to be given a line to parse. So just for the purpose of this benchmark, I guess we should have a function here which does a few different examples, maybe all the examples from that we had in our main here. Let's have a function which is we'll call bench parse temperature float, maybe. Bench parse temperature float, which is going to parse multiple temperatures. And I guess if we I hope this won't get optimized out if we do it this way, but we'll see about that. Parse temperature float, like so. So we just have a function which calls this function on multiple things. I guess we're going to assume it gives us the correct answer. So we can call just bench parse temperature float here. So what we're trying to do is have some kind of representative example. So we can call this parse temperature. The group is parse temperature, and the particular one we'll just call float, because it's using floating point parsing, like F32 parsing. Now, the reason why it's not happy is because we haven't made a brum crate yet. We've only got a main. So to make this be better, we need to make a new file called lib.rs, where we define our brum crate. And we need this function, and I guess the tests for it. I'm going to delete that sample data in a minute. So this function and the test for it are going to all live in here. And lib.rs should be recognized as a kind of top level file in our Rust, so it shouldn't need to be included anywhere else. And now our main is going to be not knowing where it gets parse temperature float from, but it's all right. We import it from lib.rs, and now hopefully our bench is happy. Let's check that running works. Yep, still prints out stuff. Oh, and look, it prints out correct answers now, which is nice, isn't it? And our tests still pass, so let's run cargo bench. Now, running the benchmarks takes a few seconds, because it actually takes 3 seconds just to do a warm-up, approximately 3 seconds to do a warm-up. Then it tries to take approximately 5 seconds to figure out how slow this thing is, and it gives us the answer. All right, so it reckons it takes 132 nanoseconds to run our benchmark. Now, that's so fast, I feel like it's going to be a problem. So something we could do is get it to do this. Give it just loads more examples. We could just live with that. Let's see whether, the thing is, it's pretty confident about the range of these, right? 131 to 135 nanoseconds. So maybe it's fine that was just a super fast thing to do, because it ran it so many times itself. We don't need to do that for it. I think that's fine. Okay. These outliers I don't know how to make it stop telling me about outliers. I don't think I really care. Anyway. All right, so we've got a working function. We've benchmarked it. Now we need to do some kind of fast implementation and check that that works too. And I guess we should also look at how to parameterize tests. Maybe. Do I go look this up somewhere? Rust parameterize tests. Let's have a quick look. Do I need to bring in a crate? Someone on Stack Overflow will tell me. Macros, no. Alright, fine. We won't do it. Fine. We'll do it ourselves. Okay, so let's just call this tests float then. And we'll have another copy that is exactly the same. We're going to hate this, aren't we? And now, I think I'm going to jump straight to my idea of a really fast way of doing this that might be terrible. Because watching, I would recommend watching Jon Gjengset's very long video, and there's a bit in it where he really goes deep on trying to get a parse temperature to be fast. And he goes into trying to make a branchless implementation of parse temperature. So let's just do a search and replace here. Branchless. Okay. So should that really be crate? I mean, I would prefer super. Either's fine, either's fine. All right, so let me do a little bit of explaining. So I've already explained that the structure of these files is always the same. There's always a digit and then a dot and then another digit, and then there might be another digit or a minus, and then there might be a minus to the left of that. And you'll notice that I'm counting from the right, because I think the best way to approach this is to walk backwards through our string, finding character by character and process them in that order. And I think I've thought of a way of doing that in a branchless way. Now, why would you care? Well, okay, what does branchless mean? Branchless means you effectively don't have any ifs, or any ifs that you do have are kind of extremely local. So the reason why this is good for performance, or should be good for performance, and we're going to measure it and find out, I guess, is that modern CPUs run loads and loads of instructions at the same time. So they're always reading ahead through your code, trying to think, can I run the next 10 or 20 or whatever instructions simultaneously? And sometimes that's possible because they don't depend on each other necessarily. And where it gets difficult is if you have an if or some branch in your code that means it doesn't know what the next 10 instructions are going to be. And then it has to guess. So it uses a branch predictor to guess what's probably going to happen, presumably based on the fact that this is the branch we took the last 100 times or whatever. So the more branches you have in your code, and especially the more times the branch predictor gets it wrong, the more wasted work there is, where the CPU tries to execute instructions ahead of time just in case they're going to be the right instruction. But it turns out it got it wrong and it wasted its time on it. So a way to make some low-level stuff like this really fast is to be branchless, which means running code that just always executes every time with no if this, then this, if that, then that. And there's a little bit more subtlety that we'll probably get to when we actually do it. But I think that there's a decent branchless way of parsing this temperature, which goes backwards from the right. I think I feel like I can come up with one, and we'll see whether we it works. Now, I've been thinking while we're doing this that probably the first thing we need to do is stop talking about strus and start talking about arrays of bytes, because I think that's just going to be unfair. So maybe even before we do this, let's have a think about whether... No. All right. Yeah, I guess we're going to compare... Oh, I don't know. Let us just jump to the right answer. So the right answer is, in my opinion, and again, not properly tested. So we can, if we're worried about this, we can make a benchmark to check these things. But I think, and Jon certainly found in his implementation that okay. Interesting. How am I going to deal with that? All right, let me finish my sentence. Oh, goodness, sorry. Yeah, that actually the best way to deal with these strings was not to think of them as UTF-8 strings, because in Rust, when you deal with UTF-8 strings, which by the way we know that these are UTF-8 strings, or at least we know that the input file contains UTF-8s, but if you're writing Rust code that deals with UTF-8 strings, from time to time, certain operations you do will panic if the string is not UTF-8, or it'll do some checking for us in some way. And we don't need those checks. We know that we can just assume it's UTF-8 and not worry about it. So the way to get bytes out of these is just going to be as bytes, I think. Yeah. Yeah, so I was trying to write B to get them as binary, and that's working for most stuff because these are ASCII characters. But for this one that contains non-ASCII characters, and what a good thing that we've got an example that contains a non-ASCII character, then you can't put a B before it to make a bytes literal. You have to turn it into bytes. Into UTF-8 bytes here, because I guess the point of the B is that everything inside the quotes needs to be a single byte, whereas here there's going to be multiple bytes used in UTF-8 for this character. Doesn't matter. The point is, parse temperature branchless, which doesn't exist yet, is going to take in a slice of bytes, not an ampersand str. And the other thing about it is it's going to return an integer between -100 and 100. And the reason why this is good is just because, like, for calculating the minimum and the maximum, it's going to be much faster to use an integer. We know that these... Oh, that's not 0.5. That will just be 5. We know that these things always have exactly the same precision, right? So floating point is not actually a good representation for them. Actually, like a 3-digit decimal, which is either positive or negative, is a good representation. It can represent all the numbers we need. We just need to remember to divide by 10 at the end. So we can even do our minimum and maximum calculations with keeping them as integers, and our mean calculation, keeping it as these integers, do the calculation, and then divide by 10 at the very end to get the answer. Or not even divide by 10, right? Just write it out with a dot before the last digit. All right, so those are things that, like, have been hard won, that we've understood that actually dealing with the raw bytes is better than an ampersand str, and returning an integer is going to be way faster than returning a floating point. Someone else figured that stuff out for us, and we believe them. We're going to implement a thing called parse temperature branchless, which looks a bit like parse temperature float, but is different. We'll do the inline never, just in case we ever care about that. So parse temperature branchless takes in, a reference to, well, it takes in a slice of U8 and returns a number between -100 and 100 will fit into a byte, so we'll have it return an I8. And we're not going to do any of this stuff. what we're going to do, now this is just my idea of how we might write a branchless implementation. Well, it'd be really interesting to see if it's fast, and whether it's faster than, maybe we can come up with some other implementation that isn't branchless but is fast in other ways, and maybe compare it. But anyway, is we're going to walk backwards through this slice. So can we get an iterator over line and then reverse it? So now I think we've got an iterator that walks us backwards. And now we want to just get some digits out of it. So we're going to have an answer. Yeah, so by the way, the reason why the answer will fit into an I8 is because an I8 goes from minus 128 up to 127, right? So we only want numbers between minus 99 and 99. Now, later, we're actually going to want to add them up so that we can find the mean. So we might end up with a bigger integer type later, so we don't have to do conversions between them or something like that. But for now, we don't care about the actual billion row challenge. We're just going to do the parse temperature challenge. All right, so let's start off with an answer. Well, no, I guess the answer can start off being the first digit, so we don't even need to start it off as 0. We can just say, get the first byte out of this list of bytes, and then in order to find an option, oh, it's an option. Okay, we're just going to unwrap it. All right, so let's just return 0 for a second to get this to compile. I guess this iterator needs to be mutable. So we're going to collect the answer in ans. And we're going to do that by finding the first digit, the very right-hand one. So in this example, this would be a 4. So this would, let's just write down right-hand digit after the dot, right? Now we're going to skip the dot. There's always a dot in that second place in from the right. So skip the dot. And there's always at least one more digit. So we're going to say ans plus equals it dot next minus. Now hang on. I haven't explained what I'm doing here. So if we've got this should be unwrap again. Now these iterators won't be none, because should we return answer? This should be an I8. And I guess we can say it has I8 here. Is that okay? Well, maybe we can start it. All right, so no. All right, we need to add I8 at the end after we've done the subtraction. So we need to explain why this is okay as well. Right. So now what we get out of it.next is a U8, which is the byte that we're looking at, and we know that in this case the byte is going to be one of 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Well, it's not going to be that byte. It's going to be whatever the UTF-8 representation of that character 0, 1, 2, 3 up to 9 is. What the encoding of that is in UTF-8. We happen to know that all those digits are ASCII, so they take exactly 1 byte. So we know that that right-hand byte is going to be a whole UTF-8 character, and it's going to be either the byte for 0 or the byte for the byte that represents the character 0 or the byte that represents the character 1, or so on. So in order to get the actual digit, like 4 in this example, we need to say, all right, what basically we know that why am I finding it so hard to explain this? We know that all those bytes are sequential in ASCII. So the character 0 is immediately followed by the character 1 and so on and so on. So what we're saying is get me the byte. That's all this it.next.unwrap does, is says get me the byte. And then subtract from that, well, however you encode a 0 in UTF-8. And then we get the actual digit, like a 4 in this example. So we do that, and we also happen to know that this number fits in an I8, not just in a U8. So let's write that down. Fits in. No, let's just write at the top of this function. The digits 0 to 9 fit into an I8, so it's okay to cast with as. I'll just say that at the beginning, and like you can believe me. All right, so the reason they fit into an I8 is because an I8 goes all the way up to 127, and we're only going to do 0 to 9 here. So the right-hand digit after the dot is very simple. We just subtract the byte for 0 from it, turn it into an I8, and we've got the correct answer. So actually, we've now done enough to make this one work, hopefully. This 0.5, we've done the 5 part, right? So the answer here in our tests, which I'll put at the top just to make it easier to see what we're doing. In our test for this parse temperature branchless, it should return 5. So now our answer contains 5, right? After we've looked at this digit. Now we skip the dot. Now we look at the next digit. So the next digit is going to be very similar. It always exists. And but we don't just want to add it on. I mean, it would be okay to add it on in this case, but in this case, we'd end up with 8 if we added a 4 to a 4. We want to add on 10 times it. So we can write it like that. Okay, so those were the easy bits, because what comes next is more complicated. So this will be next digit left of dot always exists, right? We know that there's always a digit before the dot. I'm pretty sure there is. Look, here is an example of where we might otherwise not have one, and we do have one. So the next thing gets more interesting, because the next thing could be a semicolon, could be a minus sign, could be another digit. So let's extract it out. So let's say let's call it third digit, or third. Let's call it third. So we're going to call it .next .unwrap. So now this is a U8, or it's actually a reference to a U8, and we want to do different things based on what it is. And I think maybe now we're going to do a branch here, and I'm hoping that the compiler will interpret it as a branch that is. No, we're not going to do a branch. We're not going to do a branch. Let's see. There's different ways of doing this, and maybe the compiler's clever enough to turn some kind of match statement into non-branching code, especially if we give it some kind of hint. But let's do it the manual way and see what happens. So there is a way of doing this in a branchless way, which is we're going to like put our answer in this thing called toAdd, and then we're going to do ans plus equals toAdd in a second, right? That's what we're doing here. So there's like I said, there's a couple of things that it could be. It could be a minus, it could be a digit, or it could be something else. In this case, probably a semicolon, but let's just say something else. So if it's a minus, then the following expression will be true. So the expression is going to be third. Let's dereference here. So third is going to equal the bytes for a character minus. And then what I'm going to do is take that Boolean It's either true or false, right? The third is the binary for minus. And I'm going to turn it into an I8. Now, what does that mean? I think I need to close my bracket there. What that means, now it's defined in Rust that the values true and false, when treated as a number, are 1 and 0, respectively. So what that means is, if third is a minus sign, then this 2add thing is going to be 1. Now, I actually want it to be minus 1. All right, so let's break this up. Let's say third is minus, and we'll do this part here. So this is either 1 if third is a minus, or false if third is not a minus. And if third is a minus, we want to multiply the answer by minus 1. So we've written an expression here that makes 2add be the right thing. 2_add, I guess I've called it. We've written an expression here that means that 2add is the right thing if third is a minus, and otherwise it's going to be just 0, right? Because third is minus, it's going to be 0. So that's fine. Now, if third is a semicolon or a K or some letter or something like that, we want that. We want 2add to be 0. But there is another option, which is that it could be a digit. So let's try and write an expression. Third is digit. So what that would be, now this is where things get a bit branchy, but if third is between the byte for 0 and the byte for 9, then it's a digit, right? As I8. So if it was a digit, well, only one of these is going to be true. So I guess we could say, I don't know, should we say not third is minus? I guess we could benchmark this. We could say a third's only going to be a digit if third is not minus. Hang on, we need a bracket here. Third is only going to be a digit if third is not minus. Oh, no, we need to multiply. Yeah, okay, we can do this. But there's no need. All right, so we could keep these as bools and then we'll use that thing. So basically, it is the case, and maybe we'll benchmark this. It is the case that if third is a minus, third is not a digit. And if third is a digit, third is not a minus. So now we're doing both of these calculations to figure out both things about it. And then, if third is a digit, we need to multiply third by 10. Well, no, third as a digit by 10. So I guess this is going to be third minus 0 bytes. So not times 10, times 100. And this needs to be treated as a U8, an I8. Again, all these I8s, just believe me, they're going to be... Oh no, I'm totally lying. I8 is not big enough. Because, as the fast among you will have spotted, these numbers are not between 99 and minus 99 and 99. They're between minus 999 and plus 999. So an I16, and then we might want, like my caveats about, we might want an I32 later in order to let us to add lots of them together and get an average. So everywhere I've made I8s, I need these to be I16s. Apologies. That was getting very weird. Like, how am I multiplying by 100 and this is still fine to fit in an I8? So now this line is getting complicated, and I'm going to try and explain it. So what we're at is, we've done the easy one, which was the one before the dot. We've done another easy one, which was after the dot. The next one is either a minus or a digit or something we don't care about. So if it's a minus, this number here, third is minus, is going to be 1. If it's a digit, this number here, third is digit, is going to be 1. And then we can do a little sum here to say, if it was a minus, multiply the answer by -1. If it was a digit, find out which digit it was, in the same way we've done above, and then multiply it by 100, because if there's a third digit in that place, like in this case, we want it to be worth 400, right? This 4 needs to be worth 400. Okay, so we've done the third digit. Gosh, if these tests pass, we're going to be happy, right? I mean, we could try running some tests now before we've finished and see what's missing. What happens if we run our tests? Some of them pass, so it's looking good. Negative multiple digits and negative single digit fails. I would have thought negative single digit should be passing by now. Negative single digit, panicked, attempt to subtract with overflow. Ah, okay. Interesting. So, okay. So the problem here is that third minus B0 is not allowed. So what we could do is turn them into I16s first, and then when it goes negative, that won't be a problem. It's weird because in this situation, this thing is not actually getting used, right? It's in a case where this third is a digit, so this is a non-zero number here. Then taking away the binary 0 from it, the byte representing the character 0 from it, will be fine, because if it's a digit, we know it's greater than or equal to it, so it won't give a negative answer. But because the whole point of being branchless is we're doing all of this work every time, even though we don't need some of it. So maybe this is going to be really slow. We'll see. Okay, so negative single digit still failed because we should have returned minus 13 and we returned 12. Oh, that's because I'm a fool. And we shouldn't be multiplying answer by, yeah, okay. So this is not right. This is not right. Good. I'm glad we ran our test before we finished, because we were about to replicate this problem. So, the thing we're going to add on is going to be if third is a digit, and only if third is a digit. We add in 100 times that digit. Otherwise, answer is going to be, this should really be, yeah, so we made this thing called third is minus, which is a 1 if the third digit is a minus and a 0. Otherwise, what we'd actually like to do is have something to multiply answer by. So we can call it something like sine. And sine is going to be third is minus times 2 minus 1. And what that means is, so third is minus is either 0 or 1. And, oh, that's wrong, that's wrong, that's wrong, that's wrong. Should be this. And what we want is, if third is minus is 1, then sine should be minus 1, because we're going to multiply the answer by minus 1. If third is minus is 0, then we want sine to be 1. So we can do that sum. Let's break things up a little bit. We can do that sum by multiplying it by 2. Let's say multiply it by minus 2. And if it was 1, that will come out as minus 2. then we add 1, it's -1, which is what we wanted. If it was 0, then this will all just be 0, and then we add 1, we get 1. So sine, we can calculate what the sign should be based on third is minus. That should pass all but one of our tests. Now, the last test that we've got to make it pass is when there's another digit and then a minus sign. Have we not got... How is positive multiple digits? Oh no, is that right? Yeah, okay. So the third digit is the hard one. And the fourth digit is actually easier because the fourth digit, so that would be, where are we looking here? So this is the first digit, this is the second digit, this is the third digit. The fourth digit is either a minus or it's not. It's some other thing we don't care about. So I think it's actually quite simple. We can just say fourth. That's not how you spell fourth. Fourth is just the next one. And all we care about is it a minus? Now, and this code is like it's sprawling. But I think I mean, we can certainly improve it by adding some comments and things like that. So let's have this. This will be next digit is either digit. Well, this should be next byte or next character. So we should be saying character here. So I guess these are. So the right hand character is always a digit. Let's just say right of the character. Right of the dot, sorry. So on the right of the dot, it's always a digit. The next character, left of the dot, is always a digit. Right. The next character is either a digit or minus or something else. So if it's a minus, multiply the final answer by -1. And then let's do this. If it's a digit, add 100 times it to the answer. Otherwise, I mean, where did my otherwise go? Because there is kind of no branch, but otherwise add 0. Let's just say it here. We're really going to test whether branchlessness is a good thing by doing this. All right, so now, so the fourth character, next character is either minus or something else. So we only care about if it's a minus. We should be modifying sign now, I think, to say multiply sign by the -1 or 1-ness of, well, let's make sign mutable. So I had to think about this, but yeah. So now for this variable will come out as either 0 or 1 if the fourth thing is come out as 1 if the fourth character is a minus, and it will come out as 0 otherwise. We then convert that into 1 if it wasn't a minus, and minus 1 if it was a minus. So we multiply sign by it. So normally sign will be multiplied by just 1. And then we multiply the final answer by sign. So what this means is, if the next character here, and bear in mind, by this point, like if we're in one of these short numbers, the fourth character is actually this O, not the semicolon. We've already gone past the semicolon. The semicolon case is easy, right? This is not a digit and it's not a minus. So it definitely comes out as the, in this case where, like nothing, sign gets set to 1 and 2 add gets set to 0. But this next character here, if it was a minus, if somehow one of the names ended with a minus sign, then we might end up double negating our number and getting the wrong answer. But I suggest, whoops, what did I just press? I suggest that that won't happen, that no names of cities end in minuses. Why do I call it a minus here and everywhere else? Right, a dash symbol. Let's just do that. Okay, so let's just write something about that here. We assume no city ends with minus. Now, I think that might actually break an assumption. I think the city names are just Unicode. So this might be a bug. But this is just too delicious, this implementation, for us not to try it. Right, do our test pass. Our tests do pass. Let's run cargo branch and see whether we've written a fast implementation. Bench, sorry. Now, if we have written a fast implementation, it's very difficult for us to know how fast. But what we can do is validate that it's branchless. We could try running it against some more branchy implementation. Oh gosh, we forgot to benchmark it, so that didn't go well. All right, so we're going to benchmark one of the function, which we're going to call branchless. It's going to call bench parse temperature branchless, which is going to look very similar to bench parse temperature float. I wonder, there's probably some way of parameterizing this, but I mean, there certainly is. But I would be worried we might affect performance in some way by passing in like a function, reference to a function or something like that. So I won't do that. I will just copy. Now, this one needs to be. So I guess I want to actually do this somewhere outside here. Let's call this Vishni, which is going to be an array of U8 of a length that you will please work out for me. This might not be okay because this could should be as bytes. I need to unwrap it. I don't think it's going to let me do that as a const thing because unwrapping it yeah, this is not an array of U8. This is a slice of U8. Are you going to let me do that? Looks like you're going to let me do that. That's good. Okay, so same reason as we had earlier. This one's special because it contains non-ASCII characters, so we can't just do this this byte literal here. Instead, we'll do this. Maybe there's a better way of doing that. I don't know. Okay, so let's try our benchmark again. So it's benchmarking the floats. 39 million iterations it thinks it's going to do in 5 seconds. It took 126 nanoseconds. How long is our branchless implementation going to take? Please don't take like 10 times longer. But that's exciting. It took 19 nanoseconds, approximately, which is way, way faster than this one. So I guess the thing to do would be to write some kind of naive branching implementation, but where we do the parsing ourselves, we return an integer and stuff like that. And I guess do we need to find the semicolon? Like we could still go backwards. Well, okay, first of all, let's have a look at the assembly language of our function and figure out whether it looks plausible that we have actually made it branchless. That would be our first thing to do. Because I called it branchless, but that isn't by no means any guarantee. So we want minus lib. All right, so here's the assembly language for our function. Now, before you get terrified, I don't understand most of this. So you're in the same boat as me if you don't understand it. Now, there's a few jumps in here. Now, the question is, does that mean we've failed to make this branchless? Or is it to do with, I think it might be to do with the iteration. We might actually want to avoid iteration and instead just look things up directly. And maybe that'll make it faster. So what if we called this branchless iter? And if we can get rid of, so all I'm recognizing, by the way, from like, this stuff is terrifying to me. This means decrement, I think, like reduce the value in this register by 1. This means compare something to 1. And this means, so here's a comparison happening between these two things. And then if they're equal, jump equal, I think that means. If they're equal, then jump to this label, which is down here. There's some unwrap stuff. This looks like unwrap. It's the unwraps that are causing us to jump, not the iteration. Okay, that's useful to know. I was about to get rid of the iteration here. But it's the unwraps. So is there a way of doing some unsafe thing so that we don't need the unwraps? Is there some kind of next unchecked? No. All right. So I think we are going to need to get rid of the iterator, I think, to do this. So this is going to be parse temperature branchless iter. At least it gives us some things to compare, huh? So that's good. And how is that not broken all our code? It's broken at least this one. So let's copy all this and make sure that the branchless iter function still works by everywhere we've got parse temperature branchless, we're going to change it to branchless iter. And we've still got the one without all of that in, right? Yep. But that function, this testing function doesn't yet exist, so let's have another function. It's such a long function, isn't it? I'm sorry, we never write functions this long in my videos. So this one's going to be branchless without an iter, and instead of the iter, we're just going to get hold of characters in the old-fashioned way by looking them up in line, but we're not even going to do it the old-fashioned way. So what I was going to say was we were going to do line brackets. Well, I guess we need some kind of counter. Yeah. Let counter equal line dot len minus 1, and then we do line brackets counter like so. But even that, so then we won't need the iterator, right? Even that involves bounds checks, right? It's going to check whether counter is a valid thing in line. But we know that counter is valid. We know that line is non-zero in length. And so In fact, I'm going to say we know that every city has at least one character in its name, so none of these things need checking. We can just walk backwards. So what we can do, instead of using that, which will check and then panic, is we can do get unchecked counter. Now this does some kind of multiply, and this needs to be unsafe. And I guess we should have a safety comment. So safety. We know line has at least it has at least one character of city name. I think we can assume that. I think it's implicit. A semicolon and 3 characters of temperature. So we can count back from the end. What is that? 1, 2, 5 characters, which is what we do. Now that's a general safety comment for the whole of this function, and that's all you get. Sorry. Come on. Oh, right. I never set up my cargo format the way I want it. I should have some kind of script for doing that. It would make me happier. All right. So now we got rid of the iterator. We have this counter. This counter is going to be mutable because instead of going next on the iterator, we're going to make the counter smaller. Oh, we should say minus equals 1 because you can't do that. Minus equals 1, like so. Okay. And then skipping the dot character just means reducing counter by 1. And then we're going to just, every time we do something with where we previously called it dot next, we're going to make the counter 1 smaller. Actually, we don't even need to. We're done there. So here is going to be this thing again. Like so. And all right, this time we're not doing the minus B0, but otherwise it's the same. So it's just this part we need. Good thing we got tests because I'm starting to get confused. So what is third now? It's a reference to a U8, so we need to dereference it. Like so. And one more place where we do the same thing. And we've already made the argument for why this is safe to do. We count back from, we're on the last character. Then we go back 1, 2, 3, 4. So the 5th from last character. We've already made the argument there are at least 5 characters. So these get unchecked will always get us back something, assuming our lines are in the format we expect. And certainly in our tests that's the case. So if we parse, if we run our tests, we have got tests for the branchless, which is this code we've just been writing. So hopefully we've got rid of the branches to do with the unwrapping on the iterator. So let's run our tests. I seem to have copied our tests. Our float tests. Test branchless. Test float. Test float again. Well, that doesn't seem right. Maybe I copied the whole thing twice instead of... So we've still got the test for the branchless code. We run the tests. Look, our branchless implementation. Our tests really are using this branchless code that we've just written, hopefully branchless, and it works. So I guess we should run the benchmark against this. I guess, well, what we've lost out on is actually the branchless iter. So at least we've got something to compare now. So let's bring in the function and make sure that branchless iter is one of the things we test. Run our benchmarks again. At some point we're going to get bored of running the benchmark for float, I guess. Right now we'll leave it in just to make us feel good that our code is so much faster. Now notice, by the way, that there is some variation here. So Criterion is actually telling us that our float implementation has got slower. Now I'm pretty certain that our float implementation is exactly the same speed as it was before, but something different is happening on my computer or something like that. So it's telling us it's regressed. So there is some unreliability to this. All right. So now look what's happened here. We changed the implementation of branchless, and we kept our old implementation as branchless iter. And Criterion is telling us that the performance has improved by 28% by removing those unwraps. So look, that looks to me like that is a pretty fast parse temperature function. I guess I'd like to write one in a more classical way and do a comparison, but I'm really happy that we seem to have, by removing branches, we seem to have made a difference. That implies to me that this branchless implementation is not bad. I could be totally wrong, but let's validate our assumption that there are no branches in that by looking at the assembly language for our function. It wants us to say exactly which function for some reason, don't know why. Oh, I guess because the name is let's rename it, because right now that's really irritating. So let's rename this function to just iter, even though that's a little bit of a bad name. While we're doing that, let's rename that one as well. So now if we go back, we can see now there's a parse temperature branchless, and there's a parse temperature iter, which is kind of attempting to be branchless. All right, now give us the, we need to build, I guess. Maybe we need to build non-release to see. Why is this not working as I expect? I feel like that thing doesn't exist anymore. Parse temperature branchless iter. So why is it still offering it to me? I feel like I've not compiled it or something like that. Or maybe the name is still there somewhere. So we've got parse temperature branchless, parse temperature iter. And that's what they're called here. Oh, maybe I just hadn't saved. Could that be it? All right, my test still pass. There we go. Okay, fine. Right, apologies for the confusion. All right, so here is the full assembly language of our function, parse temperature branchless. And when I look here, I do see some comparisons, but I don't see any jumps, right? And it's jumps that hurt us. So jumps tend to start with J. And you can compare things, and then if they're not equal, then you can set something. I guess that's what this is doing. That's fine. The compiler can predict the future with all these kinds of statements, so long as there aren't jumps, like conditional jumps in there, which there aren't. So I would argue that this is faster because it doesn't have jumps. Now, it also looks like it's fewer instructions, right? All these places where we're doing these checks, these are additional instructions that are being run. So maybe that's why it's faster, just that it doesn't have to do all those checks. Either way, it's coming out faster, which is really pleasing. Let's do one more thing, one more implementation, which we'll also need to pass our test. Gosh, copying and pasting these tests just seems absolutely terrible, doesn't it? Why am I doing it? I can't be bothered to think about it, that's why. So, let's do it one more time. No, not the float tests. Let's copy the branchless tests. And let's just do a kind of naive implementation of find the semicolon and go through looking for a minus number and stuff like that. So let's do tests naive. And everywhere we're running branchless inside here, we'll call naive. And the point about the naive implementation is it takes the same arguments, returns the same return type. So, you know, it's going to be like an attempt to write this code quite fast, but without the trick of being branchless. It's going to have branches in it. So first thing we're going to do is we're going to find the semicolon. Is that bad? Because is that kind of cheating? Because the other implementations didn't have to find the semicolon. So basically, is going backwards from the end. Yeah, well, okay, I don't care, right? I think that being branchless is cool. I think that going backwards from the end is cool. I want to write you an implementation that isn't as cool. So we're going to do it this way. So we're going to look inside line for a semicolon. Now, can you do find on a slice? Index of, or no, not that's the indexing operation. So is there a find? No. There's an iter.find. Maybe I just need that. No, that takes a predicate. So I guess there just isn't a good way of looking inside a slice for something that equals a certain thing. Is that right? That's pointer range. Chunk by. Split. Oh, hang on. We can do split, right? Would split be good? Can we split? Yeah, we can split. Oh, we can split out, but we need to do a find first, yeah. I don't really need to split. We won't use iterators because we've already seen that iterators are slower. Let's just, oh no, but if we use iter.find, we're already using iterators. Shall we do a loop? Would that be mad? Or is it? No, okay. I'm tying myself in knots. We're going to go backwards. Is that? And then we're just going to write this with branches, and we'll see whether maybe the compiler is really smart and takes out all our branches anyway, and it has the same performance as the others. And maybe I'm not even doing what... All right, I keep changing my mind, whether I want to compare a branchless with a branchy or a super optimized with a naive. So I called this naive. Let's do it naively. So we'll look for semicolon by iterating, calling find, and looking for a character. Well, a byte, I guess. that is equal to the semicolon byte. The byte that we're in UTF-8 is a semicolon. And now we've found that, and we can actually unwrap that because we know there's always a semicolon. Let's expect missing semicolon. Now that should be dereferenced to let us compare it. I mean, it's a reference to a reference to, so I guess we could. Oh, that's fine. It's fine. Okay. So now we found the semicolon, so let's start there. Hang on, what does find return? It returns the semicolon. That's no use. That's no use. Hold on. We don't want find, we want, I guess we want like a sort of until, skip while. We want to skip while. Oh, look at that. That's what we want. So we want to skip while the byte is not a semicolon. Like so. Should be a B, and should be dereferencing. So now this is, let's just call it an iterator. It's going to be mutable. And so now we have an iterator that's on the semicolon. So let's just skip the semicolon by saying it.next. Now the first thing might be, after the semicolon, there might be a minus sign or it might be a digit. So let's go for and sign. So let's get the next character. I guess where do we want to set up answer? I almost feel like that should be right at the very beginning. So we're going to get the next character. Equals it.next. And if ch is a semicolon, no, is a minus sign. I think that ch is a reference to a. So let's, we're going to unwrap it here. So if the character is a minus sign, then sign is going to be -1. Otherwise, sign is going to be 1. We'll do that. Is that... I tell you what, this is a little bit too similar to our other implementations. Let's do something different. Let's say, let character 1 be that, and then we'll just at the very end, before we return answer, we'll say if character 1 was a minus sign, then multiply answer by -1. And do nothing otherwise. So, oh look, an optimization, right? So we don't need this let sign. So if character 1 was a minus, we'll multiply by it. Otherwise, if it's not a minus, so I guess we need, is this just really deliberately inefficient? It's not that inefficient, is it? So if the character is not a minus, then answer should have added onto it. Hold on, we want to loop through all the characters, don't we? So we want to do some kind of okay. This is going to feel more like a more like we're actually writing a kind of naive implementation. We skip the semicolon, then we loop through all the characters remaining in that iterator. Now we don't need to unwrap on this or anything like that. We got an answer that we start with here, and then let's do a match on the character. If it's a dot, then we do nothing. So I guess if it's a minus, then I guess we are going to need a sign, aren't we? All right. So sign starts out as 1. If we find a minus, then we modify sign to make it -1. It should be a B, right? We probably need to dereference ch. No, all right. Ch's already been dereferenced, I guess. Is that right? What is ch? No, it's a reference to a U8, but I guess we're allowed to match it against a U8 here. Otherwise, if it's from 0, I think we can do this to 9. Then we're going to add answer. Add it to answer. Like so. So answer is going to be an I16, which is going to mean that it's going to complain at us for doing that, because we need to turn it into an I16. So where have we got to? Otherwise, is it bothered about how the character might be something else? We'll find out in a minute. And then I guess we'll multiply by sign here. Now this isn't quite right. Yeah, okay, it is going to moan at us. Otherwise we do nothing. So there's a bug in this, which is that we need to first multiply answer by 10 and then add on our new character. And I think that works. Oh, that's not how you write that. Yes, it is. Yes, it is. We need a semicolon here. That's why we're not getting syntax checking and stuff. Okay, good. All right, so is this right? Well, I guess let's run our tests. And the first indications are that it's right. Did we test naive? Yeah. Okay, so it looks like naive is passing our test. Let's double check that naive test. Well, I know. Let's break it and check the test fail. That would be the best way to check this code's really getting run. Yep, that didn't work at all. So it looks like our implementation is good. So we find the semicolon, skip the semicolon, then we loop through all the characters, and if we find a minus sign, we negate the sign, and we know there's only going to be one minus sign after the semicolon because we can be very sure about the format of this file. Otherwise, if it's a digit, multiply the existing answer by 10 and then add on that digit, and that will work, right? That we get what we want. If it's a dot or anything else, it can only be a dot. Then skip it and do nothing. So it looks to me like parse temperature naive is a decent naive implementation, and like it's a lot easier to understand than this mess up here and this mess up here. But goodness me, is our thing fast? We hope. All right, let's check. So let's have parse temperature. Why is this thing called bench fibs? Let's rename that to bench PT, because I don't want to write parse temperature. All right, so bench temperature naive is going to call parse temperature naive on all these. Please be slower. Please be slower. Bring it in. I guess we could do one more check, which is a branchy but otherwise non-naive implementation, just to check whether this branchless thing is actually really true. Let's have a look at parse temperature naive in assembly language. Look at all these jumps. Look at all this assembly language. Jump here if this is this. Jump here if this is this. Jump here if this is this. Okay. Now, there's also a lot of instructions, right? So really, we're not comparing like with like anyway, but let's have that benchmark run and let's think about what might be a decent implementation that is like as smart as this branchless one, but so doesn't use iterations and stuff like that, but has branches in it. I mean, maybe the compiler will be so smart it'll come up with a really clever version. Oh, we're still running our thing. So let's wait and see. Let's wait and see what comes out here. So we're doing branches iter. Now we're doing naive. You get a little hint at what the answer is going to be because it tells you how many iterations it's going to do that it thinks will take 5 seconds. So look, our naive implementation is, what is that? It's like 5 times slower than our nice fast branchless one. So let's try and be clever. We're going to, don't worry, viewer, we are going to stop. But we're going to stop as soon as we've tried a branchy version of branchless. So let's call this parse temperature branchy. We're going to try and use all the tricks in the book except we're going to branch. So, like we're going to use get unchecked and stuff like that. But it's just going to be, there's going to be some ifs in there. And we kind of unrolled this whole thing, which means we're doing extra work, arguably. If we do a really equivalent way of doing this, then I reckon the compiler might help us out and make it still branchless. So let's try that and see what happens. See whether I'm right. So first of all, first character is always a digit, skip the dot. Next character is always a digit, no branching. Now, here is a situation where it could be one thing, could be another. So we get hold of the third character and we can write an if. So if the third character is a minus sign, well, let's just say let sign equal this, otherwise this. So if it's a minus sign, sign should be -1, otherwise sign should be 1. And now we don't need this thing. And now we can actually make this an else if, so this kind of feels better. Can we? I guess we can say, no, let's do this. Let the sign be 1. If it's a minus sign, then sign equals -1. Otherwise, if it's a digit, else if this stuff, we don't need a rest break. Else if it's a digit, then we're going to add on to the answer. So I guess we can have all of this stuff in here. Not all of this stuff, but let's move it in and we'll fiddle with it. So it's going to be grab the thing as, we can just add, we can do this all in one. If it's a digit, and there's no otherwise now, like we don't need, I mean we could say otherwise do nothing, right? Otherwise do nothing. So let's just check that through for a second. So sine is 1. If it's a negative sign, sine becomes -1. Otherwise, now this otherwise is quite nice, right? It means that we don't do extra work of figuring out all of this greater than or equal to stuff if we already know it's a minus sign. So in theory, this should save us some work. But I expect that in practice this will be slower because we're doing branching, and I'm now thinking probably the compiler will emit jumps, but we'll see. Okay, so get hold of the fourth character, and then if it's a minus, then sine equals -1. That's it. And again, we didn't have to do all that arithmetic about times -2 plus 1. So in theory, this should be quicker. But I think it's going to be slower because it's branchy. So parse temperature branchy exists. Let's copy our test just one more time. And next time we should definitely think about how to parameterize tests. Test branchy. So everywhere in here where we use naive, we're going to use branchy instead. We're going to run our tests and check that that new implementation works. Let's break our branchy implementation to check that we've really actually done something. What should we do? We start in the wrong place. Yep, all the branchy tests failed because we started in the wrong place. Put it back to right, all the branchy tests pass. Looking good. Let's run a benchmark. What should we do? Let's not do float. Let's just do our really fast one, our naive one, and our new one, which I'll do first. Branchy runs this thing called branchy, which runs this thing called branchy. Here's where we find out that actually I was talking rubbish, and this one is much faster. I guess we can do cargo ASM parse temperature branchy and have a look where there's branches. I see one, so what have we got? So we've got a load of stuff that is non-branchy. Then we've got this thing which does a jump, and this thing does a jump. Now, by the way, and they both appear to jump to the same place, which is interesting. I don't know what any of that means. There's no loop, so it's not just jumping to the end of the loop, but it is doing some branching. Now, what we don't know is how predictable these branches are. Maybe they're super predictable, in which case they're not really very expensive. Let's run our benchmark. Now, I was just complaining about us not running a couple of benchmark functions, which is fine. So our branchy implementation is down for 12 nanoseconds. Our branchless one is getting 14 nanoseconds. So I guess my top theory would be, even though it's got some branching in it, those branches are easy to predict, and that's why it's faster. So isn't it interesting? I mean, the implementation is so much easier to understand. Isn't it interesting to actually measure things and have our assumptions challenged? Because it looks like our winner so far is this branchy implementation. Now we could have cheated a bit and had it be a loop like in our naive one and check for stuff you don't need to check. So where's our naive implementation? So our naive implementation always checks for a minus sign, even when we get over to the fourth one, which we know, and it has to do all of this kind of match business, even just to find a dot and skip it, even though we always know exactly where the dot is. So this implementation is cheaty cheatily slow, really, if we're really thinking about what we know about the distribution of the numbers. And then the iter one, I guess we can just reject because it does have branches. It was our attempt at being branchless. Here is our branchless implementation. And we can see it's quite a lot of code. And that's probably an explanation for why it's a little bit slower. Like, it's super fast, right? But it does appear that using all the same cool assumptions that we had, which is like the last character is always there, the next one is always a dot, the one after that is always a digit, then we get into stuff that's interesting. Then here we need, we do a bit of like hoop jumping, a bit of arithmetic to avoid writing the word if in our code. And as far as I can tell, that does actually result, that does prevent us from having these jumps, these conditional jumps. This means jump equal. So basically, we compared this thing with 45. That's interesting. Why do we compare it? Oh, I guess 45 is like where the 0 byte is. So this looks to me like it's doing the match statement. We didn't have a match statement? What did we have? Yeah, we had this match statement here. Where? Here. On this third digit. So on the fourth digit we did a equals. On the third digit we didn't have a match statement. I apologize. We had this if, and then we had this else if. So that looks to me, and we could annotate this better, but it looks to me like we're comparing with 45, which is probably saying, is this a minus sign? If it is a minus sign, jump to here. And then we do a comparison between something and 10. And I don't know what A means. We also jump to the same place under some circumstances there. Otherwise we do this stuff. Yeah, I'm starting to doubt a little bit that I'm saying sensible stuff about what this is actually doing. But anyway, we have these jumps, but I guess they're quite predictable. I can't believe they are predictable, because sometimes this is going to be a minus sign and sometimes this isn't a minus sign. So I don't think it's right to say these were predictable. I think these two bits of the if and the getting into neither bit of the if, I think they all happen fairly regularly. So I'm afraid I don't have a working theory as to why my branchless implementation is a little bit slower than my branchy implementation, other than that I've wrote more code in branchless, and being branchless is obviously not the be-all and end-all of performance. Let's run it one more time, just to get another data point. But it seems pretty confident, doesn't it? Because the 95 percentile range, I assume that's what this is definitely not intersecting with this. It's close enough to cast a tiny bit of doubt. Let's run it one more time. We get very similar numbers again. We'll run it again. So, well, that was fun, wasn't it? We implemented a way of parsing temperature, which seems pretty fast to me, 12.5 nanoseconds. The implementation I expected to be fastest, was second fastest. And the fastest one uses everything we know about where the digits are and what we can assume about this string, but doesn't go out of its way to avoid branching by doing that kind of extra arithmetic of multiplying by -2 and adding 1 and then multiplying that by something, but actually just uses an if. And that does, I'm pretty sure, come out of some actual jumps in the code. But I don't know, maybe my CPU doesn't do branch prediction, or rather doesn't work the way I claimed it does, or is able to use able to predict the branches successfully, or takes both branches, or does speculative execution, or something like that. The branches don't seem to be a problem. But we did manage to write some fairly fast code, certainly compared with a naive implementation, and certainly much, much faster than parsing as a floating point, which would be the kind of natural implementation of this. So I think that puts us in a decent place for, if we want to do more of the billion row challenge, and do let me know if you enjoyed this, then we at least have a decent parse temperature implementation. Let me know your thoughts on all of this wild speculation that I've been doing. Hope you enjoyed the video. There might be more billion row challenge. There might be more arbitrary precision arithmetic, or something completely different next time. See you then.